Dear colleagues, I also want to start by thanking the organizers and especially Peter for this invitation and to get this possibility to speak something about our studies. Let's see how it connects to your studies then eventually. Something about organic thin films. Actually, the main title was given by the organizers, but it surprisingly well describes what I have been doing. Self-organizing molecular films which catalyze chemical reactions. So I just added a subtitle, lipid interactions in biomembranes, and then maybe something also about natural fibers. And I start by defining the molecules that we use. They are surfactants, surface active agents, and they have the simple property that they are built up of hydrophilic head group, hydrophobic tail in their structure. Typical ones are phospholipids, fatty acids, most surely familiar for all of you. So that these kind of molecules have a special property that when they are introduced at the liquid air interface, then these surfactants orient at the interface, the hydrophobic tail towards the air, and then the hydrophilic group of course into the liquid. And by this way they build a monolayer, a monomolecular film at the air gas, or at the liquid gas interface. And this is the technique by which we study these films then. And the system actually is called a Langmuir. Because Langmuir is the main component. And a Langmuir barrier actually the whole system is called. This has a quite long history back. Irving Langmuir studied these systems already in 1920s and 30s, and actually he was also awarded a Nobel Prize in 1930s for these studies. And then he started by continuing the work with Catherine Blodgett, and so they developed together films that are called Langmuir-Blodgett films. That means then also these films can be transferred from the liquid air interface to a solid substrate. So, but simply what all this is about is that the sample solution is introduced in the subphase. It can be simple water or some including salts also. And then the solvent evaporates so that we only have then eventually the surfactants left at the interface. So what we then first have is a system that looks like this. We have very few molecules per unit area there, so that we talked about a gaseous-like state there. And what we actually can measure is a surface pressure. That is the difference then between the initial surface tension and the one after introduction of these molecules, because the introduction of these molecules then decreases the surface tension. And that is measured by the electrobalance that is visible there. And then what we start doing in the following is we start controlling the density of this system by simply moving this barrier. And when we simultaneously measure all the time the pressure, the surface pressure, then actually we measure the interactions between the molecules. And we obtain this kind of a compression isotherm. Isotherm because we have a constant temperature throughout the experiment. And as you see then, when we decrease the area available for the molecules, then of course the system becomes denser and denser, and we see clearly what kind of phases we have in the system during the compression, also phase transitions. And eventually we end up at a system that looks very much like a condensed film. Actually, in the best case, the solid-like state is what we gain. So the interaction of the molecules depends, of course, on many things. The structure of the molecules, first of all, of course, temperature is one thing, and then, of course, also the composition of the subphase influences the interactions. So what we eventually have is control over the packing density and orientation of the surfactants in this kind of system. Very nice model system. And especially very nice model system for biomembranes, because that is what this is. The analogy between these Langmuir films and nature is that our monolayer is half of the lipid bilayer of a biomembrane. That's what it looks like normally. So that, for example, then systems that can be studied or phenomena is like here demonstrated transport phenomena through this kind of films. Even if we have only a half of the structure, we can still use this system as a model to study also biomembranes. you can think of many systems that we can study with this armor films. Drug release, for example, biocompatibility of implants, if you wish, and so forth and so forth.
You guys mentioned the difference between the S and LC state. I didn't see why the pattern was also in S state. One before pattern.
Actually, we see it here also. Well, maybe not so clear. Anyhow, LC is liquid crystalline or liquid condensed, and the solid one is really solid. So liquid crystalline is less dense. It has a clear structure already. You can find out the crystalline backing. It's well ordered, but it's not as high dense as a condensed phase.
The geometry changes. So the geometry changes.
The geometry obviously changes when you go over finally to the condensed. Yeah. There are groups that have studied this, the exact structure by crystallographic means, also in situ at the interface and as a deposited film, and they have demonstrated many different structures for one type of molecules, simply as a function of pressure, as a function of compression. Yes, so this is to demonstrate one type of a typical lipid, and now we have studied the compression as a function of temperature. So obviously, of course, pressure is one driving force that controls this system, the density, but also temperature is one very important one. And as you see, as the temperature increases, of course, then it results in, if not anything else, then in increased thermal mobility of the molecules, and that means then that more energy is needed to compress these molecules together. Of course, we have to keep in mind that this is not a system in chemical equilibrium, of course, because we put in energy by moving the barrier forward. So if you take the barrier out, it's not a chemical equilibrium, it will collapse. So this is an artificial one, of course. So similar, we can again take an example from nature how this relates to nature. Let's think about the body when you get viruses in your body. What happens? The body wants to get rid of these viruses, of course, and how does it do it? It increases the temperature, of course. That means you get fever. So that's exactly what happens then, is that the system becomes slightly loosened. Getting a fever means that the density of the membranes slightly decreases, and that, of course, accelerates transport of matter. So this can be demonstrated here, for example. In a biomembrane, a typical surface pressure that appears there is around 30. So you see a small increase in temperature here, slightly decreases the density factor. That means increases the mean molecular area here. So the molecules become slightly more mobile, and that's what is accelerating the transport of matter. Then we may proceed with this processing these films, and as I said, then it's also possible to transport or transfer this film from air liquid interface to a solid substrate, and this can be, for example, simply done by this kind of a technique. We have a solid substrate that simply is brought into contact with this film, we let it react, and then lift up, and then eventually we have a film adsorbed, attached to this substrate. I'll come back to this, how this can be actually controlled, this interaction here. So what we have after deposition? Of course, we have an original surface that has become modified through changed composition. Of course, for example, in the previous case, we had first a gold substrate, now it's covered by lipids, so it's totally different by composition. Surface chemistry and energy has been changed, of course, and obviously surface reactivity. And I'll also get back to this, how we can actually quite exactly tune the reactivity. So what we have is that tailor-made surfaces can be made through molecular architecture and then also controlled processing. So let's get back a little bit more into the details about how our film, particularly the film that we studied, looks like. As you see here, we have a bilayer, a film consisting of two different types of lipids. This one with the red polar head group and this one with the green ones. So let's first take a quick look at the matrix lipid, that means this one. So the function with this one is obviously to get as high adhesion as possible against the substrate so that we can then produce a highly stable structure. What we have used as a molecule is this kind of very complicated name. We call it shorter than DST-PPC. So actually it has the main structure resembles that of DPPC, that's very well known lipid. But what we have then done is that we have, through synthesis, introduced a disulfide end group at the end of one of the hydrophobic chains. What that means then and does and gives a function is that it enables covalent binding to the metal substrate. In our case, we use gold. And by this way, we can get a very stable structure for practical applications there. And so in this case, we have not modified this end group at all, but actually we don't need to modify it neither because this provides a very low reactivity against proteins, and that's what we want for this component. Because we have the other component that has the typical that gives the biofunctionality for the structure. And there's two examples that we have studied. The first one is this kind of lipid where we have a lightweight functional group introduced in the polar head group, so that this enables the study of lightweight antibody fragment interactions and binding phenomena. And this eventually then can be used to study the real interactions that we are interested in, namely between antibodies and antigens. Another molecule of interest that we have studied is this biotin derivatized lipid, and this is of course then suitable for studying reactions between biotin and steroid. So that eventually we have this kind of a structure. We have a lipid, bilayer, consisting of two different lipids, the matrix and then the biofunctional component, and in this case, for example, functionalized with the biotin intermolecule there. What is also important to realize here is that the two lipids that we have here, the matrix and the biofunctional lipid, are similar enough, so to speak, so that when we make this film, no phase separation occurs. So that a lot of attention has to be paid here. Because if we have a phase separation, then these all would end up in the same position, and we don't have the homogeneous functionality then anymore. But the chains are more or less the same for both lipids. That's why the risk for phase separation can be remained pretty small. Well, in order to be sure that we actually have succeeded in this, it's nice to demonstrate that all this is there and is functioning well. So we use, for example, AFM to demonstrate this by taking topographs with AFM and we get then molecular resolution and actually can see where, for example, in this case, the immobilized streptavidin molecules are. We have in purpose had very low concentration of these in order to be able to see individual molecules. We can increase, of course, the yield of adsorption if you want by increasing concentration of these in the solution. So indeed, well, this is a little bit too large, the lateral dimensions, but the height information is very reliably obtained by this technique. So we can read out where our proteins are on the surface, we can read out their dimensions, especially height, and we can even calculate the yield of adsorption. And we can make the same kind of analysis for fat fragments, for example, that have been immobilized there. Now we have a clearly high concentration of immobilized molecules. And since we then really have quite homogeneously distributed these linker lipids, then we have a quite even distribution of these fats at the surface. And we can again read out their dimensions, especially height, from the height profiles here. That's possible because we have a very, very flat substrate as a reference, and also the lipid monolayer is flat enough, which gives the possibility to read out where you have the proteins there. Obviously, we don't want the ITG to be immobilized on these empty spaces here. So we have to block out these, and then we use, for example, BSA to block these empty spaces. So that eventually then the ITG comes and reacts only with these ones. And this is the very specific reaction that we are looking after. So what I have demonstrated is that we can quite in a controlled manner produce functional surfaces. We first have a very smooth substrate, then we have a matrix monolayer which is highly stable and it's of high quality also, it's covalently bound to the substrate, and also if only having a pure matrix lipid, then it has a very low reactivity against proteins. Then we introduce the biofunctionality there. We have also high quality of this, because even if these molecules are not covalently bound here to the substrate, they are through the pressure within the film strongly enough bound to the matrix, and that guarantees that they don't diffuse away from the film. And we have then high reactivity and especially specificity against adsorbed biomolecules. Also, we continue immobilization of biomolecules. We have a homogeneous distribution of biomolecules, and we have a selective reactivity against the analyte. And eventually we can detect the analytes then successfully. So what we have been able to create is a biologically sensitive element. And this is through understanding the function, the structure and function of the lipids, processing them in the right way, and so forth. So the rest is then more or less technical, and I don't go into the details maybe here, but I just want to say here that we have just created this biologically sensitive element. We have some either chemical or physical property or change or factor that changes during this adsorption here, which we then transduce to a signal, which can be there are several possibilities to detect that signal. Then I go over to natural fibers. I mean, there is certain things that are very common to what I just talked about. Obviously, for a paper chemist, the goal, the aim, is to get paper of as high quality as possible. There is, of course, many properties according to which this can be optimized, this whole project, the process, and there are many steps here. But obviously, it must be this one, the raw material, that actually we should understand the structure of wood that helps in optimizing this whole process. And that's why we have studied quite a lot the structure of wood fibers. That's what it looks schematically, and here we see then what components we actually have, the main components of it: cellulose, hemicellulose, lignin. There is also extractives, but they are so small amounts normally that they are not often even mentioned here, but we shall see that they have a special function in there also. So as a paper chemist, they want to optimize, of course, the yield of the cellulose component here as a result of processing, because that's the component that gives the paper the brightness, the whiteness. But then, and if you take a look at samples taken from the mechanical pumping, for example, we see that the process has been very successful in that sense, because what we see here is pure microfibrils, cellulose microfibrils, that are the small structural components of the cellulose fiber. Very small structural units, only 20 nanometers in diameter. And we can see different lamella there, and so forth. But actually the question that should be stated here, we have a very high cellulose content on these samples, but is this then enough to guarantee high quality paper? And actually, if we get back to this and look at this structure, there are, besides cellulose, also many other components. The hemicellulose is lignin and also these extractives, and they must have a clear role, clear function in these structures. So that it's a little bit stupid actually to only take out one component I think that works as such, because it has been shown that, for example, if extractives, they act as a glue there. So when you make paper, it's not enough to just have white paper, it has to have a certain strength also. So what has been shown then actually, that by introducing actually back, by absorbing, for example, typical extractives, fatty acids, resin acids, cytosterol esters, for example, by introducing these and making paper out of these, the paper becomes much more strong. So by, again, controlling the surface of the raw material, the properties of the end product can be controlled in a quite nice way. In the same way we have studied flax, this is what its structure looks like, a little bit different from wood fibers. And the processing that is used for this is usually retting, with dew retting or water retting, even winter retting. The purpose is the same, to optimize the yield of cellulose. And here is, for example, this is also exercise for your neck. To see, I wanted to optimize the size of this, so try to listen here. But the main message is that we can actually resolve very exactly what we have, what kind of components we have on the surface of a flax fiber. And what we see actually, surprisingly, that there is a bunch of extractives again, which are only less than 1% in bulk composition. But since they are on the surface, they are the components that give the main functionality for these fibers. So that when we aim at, this is only another range of spectral rays, to demonstrate this one is in one sense treated and this is another process. So we see that it results in completely different composition. If we go back here, we see that we have a lot of extractives here. If we process in a certain way, we can rid of the extractives there. What I just want to demonstrate is that when we make composites out of these fibers, we have these fibers as a reinforcing component in a polymer composite. Polymer was in this case polylactide. So as a function of chemistry, we get completely different mechanical properties. And what the message here is that values here correspond to pure cellulose. And the more left we are here, the less cellulose we have on the surface, the more we have other components. That means optimizing cellulose here gives the worst, actually, mechanical properties. So we have to have some other components also on the surface in order to get a good composite. We have studied quite a lot this, and we have eventually been able to actually then prepare, manufacture biodegradable flax fiber reinforced polymer composites. That's one of the future interests. To, for example, replace glass fibers with flax fiber. And one more thing, if we have a time?
3 minutes.
3 minutes? Okay, that's enough. Because I've so far been talking only about chemistry. Chemistry, of course, determines the main properties of the surface. But that's not all. Actually, the chemistry can be, for example, measured by measuring contact angle. So if we consider an ideally flat surface, we get something that can be described by Young's contact angle. But what reality is then is that we always have some roughness. And if we have the same chemistry, but roughness changes from here to here, we get a completely different answer here. As you see, the contact angle is like this big, and it gets smaller here. So what it means then, the roughness clearly increases wetting in a case of a polar surface. So we should never forget the structure when we analyze the surfaces. So, but this means then that the structure is also one type of catalytic factor. Well, these can be interrelated then through a topographical factor that in this case is described by effective and projected surface area and their ratio. But now again, since we have a tool for measuring 3D structure, we can actually then calculate out from for example, such an image, one certain roughness parameter and obtain this one, and then evaluate our real chemical nature of the structure through measuring the real contact angle for sample with some real roughness. The case is completely opposite if we have a non-polar surface. Again, more model surface and real surface. So as you see here, the contact angle is clearly increased. And one special case is very interesting. The one where we have the parameter that describes now the morphology here. If that closes 0, then we have something, we have been able to create a surface that is called superhydrophobic. Such a surface can't be created by simply tuning chemistry, but you have to take into account that you have to have a certain roughness. And nature utilizes this also. This is called the lotus effect. So the lotus plant looks like this. So if we are able to mimic such a structure, we could apply this, for example, in self-cleaning glass. It's a very interesting technical application to be studied in the future. And this is the whole range. And you see how much actually the topography influences. This is the real behavior, and this is if we would have no influence from topography. So really, both factors have to be taken into account. The chemistry, the structure, both have their catalytic influence on the function of the surface. That's all. Thanks a lot.
Right, so you presented here a quite impressive example of present-day biotechnology, surface chemistry-based biotechnology. And of course we are quite far from the original life, but now we can see that it relates to the original life because it has been postulated now that we don't know exactly if this is true, but the first field of chemistry was happening as surface chemistry, where some capturing surfaces were somehow organizing and templating the reactive molecules. So even the your surfaces here are now very well tailor-made and designed to capture certain molecules, we might now here make an exercise of thinking of early surfaces which may have assembled in primitive conditions to capture certain reactants. And
water surface can act as a plate, as a substrate.
Quite common hypothesis is, for instance, the cationic surfaces of clay crystals to capture magnetic molecules and arrange them for reactive positions. Also, I've seen a paper now, but I don't remember the details of some sort of spontaneous two-dimensional arrays of purine bases, which arrange in a very symmetric fashion, except that they, in this sort of mosaic array, they can also contain asymmetric discontinuities. And it was proposed that this sort of discontinuities of the symmetric structure could have been the first spontaneous introduction of some information, which is then, by template function, copied into a polymer. Okay, and now this comes to chemistry, and I don't understand the chemistry here, but maybe you and the audience can think of self-organizing catalytic surfaces. Apparently, it's very easy for present-day biochemists to think of catalytic molecules or capturing molecules, interacting molecules. But we should think of now something very simple functioning in the same way.
Well, so I'm coming from physical chemistry and my background is in physics. So I can't comment too much about the chemistry. I think that's it.
Yeah.
So,
So this model of the two-dimensional nucleotide base arrays, of course, might be attractive because these could then make hydrogen bonding to bases also. Would Harvey see any potential for such sort of chemical arrays?
I don't know exactly these arrays or how they are.
there is a group in Tampere that applies these systems for energy transfer studies, electron transfer. So they make tailor-made molecules, but they can also use imagery existing molecules to study those. We can try to really apply them in technology. This is our order. That's the same thing. You have maybe the opposite use. You wonder where it comes from. But also we need to understand the structure to be able to apply it in some way.
I still have not understood what the title says, catalyzes chemical reactions. As I understand it right, you just should provide an attachment point or something.
In this case.
Yeah. And how, I mean, if you have catalyzers, then you need something else. It's not catalyzers, it's just keeping some molecules
We come back
in
to
a
the question.
defined orientation or something.
We come back actually to the question of what catalysis is or catalysis. We have studied polymerization in this field also. And all that is needed is to control the pressure, the density. We don't need any catalyst. Even we can polymerize unsaturated fatty acids that do not polymerize at all in this solution. Because they have a very nice order, very high packing order, and we can simply bring close together the reacting sites. That's enough. Slightly wrong pressure leads in no reaction.
Yes, this kind of catalysis is not chemical catalysis, it is physical catalysis.
Just one fact.
Pressure, temperature, and concentration are physical catalysis. And physics can also photocatalysis. And the simplest autocatalytic reaction, hydrogen chloride, synthesis of hydrogen chloride is a photoautocatalytic reaction. So it's a physically catalyzed.
I mean, we did use UV light.
Catalyzed.
Where it is, of course.
Physically
Not
catalyzed.
non-chemical catalyst was needed.
Physically catalyzed simplest form of light. The living element is photon there. And it was discovered by Max Bodenstein in 1911 and explained by Polish physical chemist Jan Zawicki in 1916, who coined the term autocatalysis, nearly 100 years ago. But none of these people and later people understood the fact that autocatalysis is the first universal principle of life, exolife.
Okay. In addition to this catalytic property of these surfaces, I don't want to have any more questions to that. I would like to mention the other aspect here, what is quite related to astrophysiology, which is the current efforts in many laboratories where people are assembling synthetic cells from simple lipid bilayers, group by Luisi in Italy and Beaver's group at least in the States, and are able to assemble already at least some semi-functional cellular-like entities able for import and export of molecules. So they are synthesizing active cells that can have replicating RNA inside of them, and these really are quite actively soluble cells. And I understand that one of the main aims is to produce nanofactories for synthesis of whatever technical products, but of course it also resembles whatever has happened in the spontaneous assembly of cells, of the lipid vesicles, which then evolve to cells. So would anyone have some insights into this mini cell biology?
Yeah, I mean, I'm on one of the projects in Europe who's doing this also programmable artificial cell evolution. It's called. It's not the same as the AD2 which is actually parallel effort. We're using a slightly simpler PMA-based approach because the PMA tends to magically diffuse into micellar structures or other hydrophobic environments. And therefore, it's easy to see how they can hitchhike on these type of self-assembly capable structures. So that's not very difficult. That's also trying to produce some artificial cells.
Would you maybe even explain a little bit more in detail how artificial cells function, or how you assemble them more? Because I think these are quite fascinating.
It's just that it takes quite a lot of time to actually do that. I mean, it's a whole talk.
Okay, not in 5 minutes. Can you make your little cells replicate?
Yes, otherwise they're not. Yes, well, no, I mean, no one is not.
Divide.
No one is not. I mean, this is the one who does that first, of course, really ways to create something in lifelines in the lab. It's nothing that will probably be done within the next 5 years. People think so. But I mean, the lipid structures do divide, but that's a spontaneous process. Because they sort of tend to incorporate more and more lipids and then they destabilize and then they divide. I mean, that's rather simple to do. But then you have to have the genetic information you put in RNA or DNA or whatever molecule you use to hitchhike on this and sort of template them to happen at the same time. That's more complicated. And probably need to connect that with metabolism, so you sort of actually connect the production of the template and the production of new building material, the lipids, so they happen at the same time, and therefore the destabilization of the templating problem happens simultaneously. Otherwise, this won't work very well. So the short answer is that it's not been done yet, but sort of the building blocks to do this has been done. But the problem is to keep it all together in one container that's this is nothing.
Keep an eye on this. The research person. There is heavy research.
So I think that one of the points which is not so often discussed is how to produce the building blocks for these polymers, whatever they are, RNA or free RNA or whatever. So it means that even if it is possible that these small molecules are created just from as you described, from carbon dioxide and these kind of things. Then if you really start to think development of life, so you need a lot of one type of monomer. And it's not possible that you just happen to take this monomer out of these dozens of different small molecules which are spontaneously created. But it needs that you must have some kind of early metabolism as well, at very early stage. So you must have a machinery which produces this building that you need. And I think this is the problem, because then we need quite a lot of information already, when we need very many catalysts, cytosines, or whatever, to produce.
So you're basically saying that if the building blocks are spontaneously produced, there is too much of everything, and too many things in this primary
Yeah,
soup.
it helps maybe in the very, very beginning,
Yes.
but then when you start to go a bit further, when you have to plan to do this and that, you need these building blocks more and more. And you must have a production of these building blocks at very early stage.
So you need to have quite high concentrations. Yes, this is actually exemplified by somebody telling of these Stanley Miller type experiments. You probably know from the 50s there was this very famous chemist who was synthesizing amino acids and all good things in these glass bottles where he just had methane and ammonia, basically, and hydrogen and water. And then he sparked this, and then it was so big excitement because he was producing a whole lot of these central amino acids with light needs in these bottles just within a few days. But actually, somebody is saying that when these experiments are done, these glass bottles become quite coated with this kind of brown substance, which is just tar-like kerogens of different carbonaceous compounds. So a whole lot of very even large organic molecules are produced in a very random mix, and it's just like tar. So probably you are just hitting this point by saying that there is just too much of randomly everything, and even compounds which are not used at all in these biopolymers. This may be quite inhibitory also.
Why should that be the case? I mean, it sounds rather surprising. I mean, you have too much of the good stuff. Are you really sure that's that kind of drug then? I mean, first of all.
So I think if you have to build a reasonably long oligomer from a certain type of building block, and you have to make copies of it, so very soon you come to the stage that you must have in environment quite a lot of this material in exactly the same way as viruses need this material from their host cell. So someone must provide what they need. And I think this also would occur, or is one threshold for the development of life, that it's not sufficient just to transfer information, but you also have to produce the material.
Yes, but undeniably this did happen, so it is just now up to the scientists to kind of try to think of how it is.
I don't say that it is impossible, but it is just one of the things that people should be patient.
I mean,
Question 2, how the small molecules are catalytically synthesized at early phase with very primitive catalysts.
what could help, of course, would be if there was some spatial segregation, which would be in a suitable way, so that the stuff that you do produce but you don't need is being moved to another location. I mean, the point is, either the atmosphere was reducing, which is not necessarily accepted generally, and then of course such products which produce amino acids, including even a few nucleotides, I believe, are unavoidable. So we have to cope with that problem and have to think of ways out of this. Or alternatively, the atmosphere was not reducing, and then of course I don't even know what is the thing. I mean, then of course I have to think of having certain of building blocks coming from space or whatever.
No, but the micrometeorites, they bring tons of organic material to the surface of the Earth.
Yeah, from space then.
Yeah, but that's not bugs, it's just the molecules.
And And the hydrothermal vents can also produce the basic building blocks.
Yeah, so it can be locally, even if the atmosphere was not producing globally, it can be local areas where you can do developing chemistry.
I have developed a minimal, system theoretical, minimal self-replicating cell, which consists of two components only, water droplet and a minimal metabolism. And this minimal metabolism is a self-replicating chemistry, that is autocatalytic, some autocatalytic reaction, whatever, which occurs is possible in the water droplet. In the solution.
Minimal metabolism requires at least 480.
No, it requires precisely two elements, whatever can function, A and B. I call them A and B, but they can be whatever reactions, autocatalytic reactions in water. Let me explain first. And then when this process takes place for some time, the water droplet becomes bigger and bigger, and then we come to Boltzmann's principle of equipartition of energy, which is another universal principle which I did not have time to explain. But it obtains, this principle obtains between the internal pressure inside the droplet and the surface tension of the water droplet surface. And once the internal pressure becomes bigger than the surface tension, then the droplet begins to shrink and divide, to cleave. That is the simplest possible cell, and it functions in reality. I leave it for you chemists to make this experiment.
What's the driving force to increase the internal pressure? What causes it?
Catalytic reactions, because it increases the number of molecules. But of course, it requires some environment. Let it be oil, for instance, or the droplet in oil. And in oil, you must have some nutrition. The components, the reactants of the autocatalytic reaction. Nothing more strength is necessary.
I think we need to break for lunch and continue for lunch the details and read